In this lecture, we take a look at the area of a parametric surface. We assume that the coordinates of a point on the surface are given parametrically in terms of the parameters u and v. That is, x is equal to x of uv, y is equal to y of uv, and z is equal to z of uv. The parametric surface could be like the surface drawn below. We write the parametrization of the surface as a vector function. Let the vector function r of uv be the vector with components x of uv, y of uv, and z of uv. We will write the area of the surface as a double integral. But first, we must find a fundamental element of area for the double integral. An element of area is like a rectangle when we use Riemann sums to find an integral formula for the area under the graph of a function. Now, the parameters u and v generate a natural mesh on the surface. This mesh or grid is similar to the grid generated by the xy variables on the xy plane. For example, when u is set to be the constant u sub I, we might get a parametric curve as shown below. And when v is set to be constant at v sub j, we get a corresponding parametric curve. Using the mesh on the surface, we use one of the curved quadrilaterals to help us find the fundamental element of area for the double integral formulation for the surface area. Let p sub 0 be the lower left corner of this curved quadrilateral. At p sub 0, u equals u sub I and v equals v sub j. Let p sub 1 be the lower right corner of this quadrilateral. At p sub 1, the parameter u will have changed, and so we let u be equal to u sub I plus delta sub I u. The parameter v stays the same at v sub j. Let p sub 2 be the upper left corner of the quadrilateral. This time u stays the same at u sub I, and v will have changed, and so we let v be equal to v sub j plus delta sub j v. We now approximate the area of this curved quadrilateral. Let the vector m be the vector from the point p sub 0 to p sub 1. We find the components of the vector m by subtracting from the coordinates of the point p sub 1 the corresponding coordinates of p sub 0. And so the first component of the vector m is x evaluated at u sub I delta sub I u and v sub j minus x at u sub I v sub j. We have similar expressions for the second and third components of the vector m. We define the vector n to be the vector from p sub 0 to p sub 2. And similar to the vector m, we find the components of the vector n by subtracting from the coordinates of the point p sub 2 the corresponding coordinates of p sub 0. This time the change is in the parameter v. Assuming that the two vectors m and n are non-scalar multiples of each other, these two vectors determine a unique parallelogram. And it is the area of this unique parallelogram that we will use to approximate the area of the curved quadrilateral. The area of the parallelogram is equal to the length of the base vector m multiplied by the height. The height is the distance between the base vector m and the opposite parallel vector. If theta is equal to the angle formed by the vector m and vector n, then we can take h to be the length of the opposite side in the right triangle where the vector n is the hypotenuse. H is then the length of the vector n multiplied by sine theta. And so the area of the parallelogram is equal to the length of the vector m multiplied by the length of the vector n multiplied by sine theta. Most of us should recognize that this quantity is simply the magnitude of the cross product between the two vectors m and n. To find the cross product between the vectors m and n, we use differentials to approximate the components of m and n. For the vector m, since the change is in the parameter u, each component will be approximated by the differential with respect to the parameter u. For example, the first component will be approximated by the partial derivative of x with respect to u, evaluated at u sub I v sub j, and then multiplied by delta sub iu. We approximate the y and z components in a similar fashion. We do something similar for the vector n, but this time, since the change is in the parameter v, the differentials will be with respect to the parameter v. We use these differential formulations for the vectors m and n and write the cross product of m and n as a determinant accordingly. For the first row, we have the unit vectors I, j, and k. The second row is made up of the differentials of x, y, and z with respect to u. In our notation, we're using the subscript u to indicate partial differentiation with respect to u. The third row is made up of the differentials of x, y, and z with respect to v. Writing this out in terms of the vector function r of uv, the cross product of the vectors m and n is approximated by the vector r sub u, that is, the vector function r differentiated with respect to u, crossed with r sub v, or the partial derivative of r with respect to v. And then we factor out delta sub iu and delta sub jv. Therefore, the area of the parallelogram is approximated by the magnitude of the cross product of r sub u and r sub v, multiplied by delta sub iu, delta sub jv. And so here is our fundamental element of surface area. And so we approximate the surface area by the double summation over I and j of the magnitude of the cross product of r sub u and r sub v, multiplied by delta sub iu, delta sub jv. Now, assuming that this double summation tends to a limit as the maximal delta sub iu and the maximal delta sub jv both go to 0, we denote the surface area as the double integral over the surface S of the magnitude of r sub u cross r sub v integrated with respect to u and v. Now let's consider the specific case when z is a function of both x and y. That is, z equals f of xy. We set the parameter u to be equal to x, and we set the parameter v to be equal to y. And so z of uv is equal to z of xy. The vector function r of uv now becomes r of xy, and this is xyz, or xy z of xy. In the surface area integral, r sub u becomes r sub x, and r sub v becomes r sub y. Both of these derivatives are evaluated at x and y. The derivative of x with respect to itself is 1. The derivative of y with respect to x is 0, since x and y are both the independent variables here. Z with respect to x is z sub x. Similarly, r sub y is equal to the vector 0, 1, z sub y. And so the cross product of r sub x and r sub y becomes the determinant whose first row are the vectors I, j, and k, The second row is 1, 0, z sub x. And the third row is 0, 1, z sub y. We calculate this to be the vector minus z sub x minus z sub y, 1. The magnitude of this cross product is the square root of the square of z sub x plus the square of z sub y plus 1. And now we have the integrand for the surface area double integral when z is given as f of xy. Therefore, as a double integral, the area of a surface given by the equation z equals f of xy is equal to the double integral over the surface S of the integrand, the square root of the square of z sub x plus the square of z sub y plus 1, integrated with respect to x and y.